Hi all, good to see you. Thanks for coming. This is Amit, and Daniel is also there. So we're going to present lending market risk assessment via agent-based modeling. Let me give you a very brief background, like why we are doing so, what's the use case of that, and so it would be a joint presentation. I've divided it into two parts. Like I'll going at the high level, and then we'll have a very deep down on what we actually were talking about. So financial stability and DeFi, like two scary words. uh, so in the beginning of a year when we started doing this actually at Polygon, we thought that this is the right time we start taking it super seriously. And then the debacle came, like a various debacle. Then we ramped up. So theoretically, like there is a dilemma of scalability and stability. Like why? Imagine like if you want to scale a DeFi solutions, you add up a lot more network. What does it mean? Okay, it means if a risk can be started at one node, it can propagate much more quickly and widely. So that's a dilemma. Like you are scaling the DeFi system, but you're also making it okay, much more risky as well. So that's a network effect working in the negative direction for the financial stability part. And you know, this financial stability is a public good. So that's why like we at Polygon are actually doing it. If the protocols in the DeFi started getting themselves stress tested, optimized on the risk framework, the whole ecosystem will benefit. So it's the financial stability which we are talking about. And what we are working on the risk assessment framework for DeFi, there are primarily three reasons of doing that. Like first one, so there are three reasons. So what happens, like, you know, it keeps on shifting according to the era. So right now, the first reason, that's a major critique from regulator and central bankers, is the first one. Like last year, it was the last one. So one of the major critique they have, like it's a DeFi is to become widespread. Its vulnerabilities might undermine financial stability, no safe for consumers. I picked up these quotes because these are like prominent quotes by important persons, without naming them, of course. Uh, and also, we really want to make DeFi system protocol robust to handle uncertainty. So the protocols itself need to evolve as a stable solutions. So for example, can risk taken by users can be concretely quantified, because there exists like users go to the protocol, do something, they are sometimes educated, they are not, but what about the risk? Can we give more information to the users, and then users can take much more informed decision? So that's what it is, the risk assessment is after. And the third, the most important thing, I think, if you are in the DeFi world, capital efficiency is the like very common word. Over collateralization is seen everywhere in DeFi. And what risk management framework can do in DeFi, you can like dynamically reduce the amount of collateralization. So optimal decisions can be taken. So that's what, you know, the risk assessment framework is all about. I'll give a very brief overview what we are talking about in high level. We decided like I talk high level and Daniel like really deep down, because apparently he has more postdocs. So, so if you see in the center, like is a DeFi protocol, it's a very complicated universe. Like that's a real graph for the DeFi protocols, which you see the networks, like the curves, Uniswap, everything. And in this DeFi protocols, what we are trying to build is around a resilient shell around it. This risk assessment will act as a resilient shell because our risk assessment engine can take modeled uncertainty into the account. By modeled uncertainty into account, like some external behavior in the outer side market, which is causing some potential shocks to the DeFi protocol. Once we assess the protocol's risk, the risk engine throws you some of the parameters, like you can do option 1, 2, 3, you have to optimize this. Then we need to implement a risk and management solution. Now the onus lies either on the DAO or the protocol people or the community. Like, it's an open-ended question. But then what I'm trying to explain here is the whole cycle. You stress test the protocol, you implement the risk management solution, you monitor and review it, and you keep on doing it for certain times, and then your protocol become like really robust to the market uncertainties. So we take the agent-based simulation framework, but and the protocol which we stress test is OVIX protocol. So one of the good benefit about stress testing is like you can really focus on this, focus using the simulation pre-launch. So that's what the really important. You can do it post-launch also. You can do it on any of the lending protocol, compound AV, but self-optimizing protocol even before the launch is super important. So in this model or the framework of ours for the lending protocol, there are two agents, borrowers and lenders. They're clearly shown like borrowers and lenders here. So there are various types of borrowers. The complication here is like every borrower is of a different type. It leverages at a different level. Their amount of collateralization is different across different scenarios. So like we try to model it in an agent-based simulation model. In the center, there is risk management happening. So it's a framework which one of the main USP of this approach is agent-based modeling, which actually central bankers always dream of doing into the real economy. So the smart contract has deterministic kind of outcomes because it's a written code. So we can actually precisely model it using agent-based simulation behavior. And so we have come up with a paper. It's on, I think I'll share the link. So it's a multi-asset agent-based approach. It's a, like it's a math and all is everything written down there. And Daniel, I think will try to explain some of the graphs which you can gather and see and the usefulness of use cases of that. The whole idea is that it's like we're trying to get it in the very general framework approach, and so that any protocol on Polygon chain can really risk assess them. We are moving towards some of the usability of that in terms of front ending or something like that. Yeah. So if you are interested, or you're and you have in your network who have protocols or DeFi protocols, do connect with us. Like, we'd be happy to chat about this. So go to the Daniel there.
Thank you, Amit, for the nice introduction. I don't know if it's a compliment to have more postdocs personally, but I'll take it from here. So we've published a paper where we explained the technicals of how you stress test a lending market. So at OVIX, we are a lending market with a V-tokenomic, with our plan on the roadmap to introduce V-tokenomics to bootstrap liquidity to the protocol. What is a lending market? I don't know if you've been living under a rock and have never seen a lending market before. So a lending market is a place where people come and they lend crypto assets, and they have the possibility of borrowing crypto assets against those crypto assets. And the kind of users that come onto a lending market can be very diverse. So here in this example, Alice has a bunch of stable coins, and she just wants to gather yield on her stable coins. So she comes on our lending market, she deposits her stable coins and just collects yield over time. Bob comes around, and he's a MATIC lender, okay? So he has a bunch of MATIC tokens, he lends them, and he uses that as collateral to borrow, let's say, USDC on our platform because he knows of some other yield generation scheme off the lending market, and that's what he's into. Charlie and Devon come around, and they're respectively, one's a Bitcoin maxi and one's an Ethereum maxi. So Charlie comes and basically creates a leveraged long position on Bitcoin by using Bitcoin as collateral to borrow stable coins, which he swaps for Bitcoin, which he redeposits on the platform, and so on and so forth. And Devon is playing the flippening. So she's depositing Ethereum, borrowing Bitcoin, swapping it for Ethereum, and basically creating a leveraged long Ethereum versus Bitcoin position. The point is that, and then on top of this, once the V-tokenomics get engaged, we also have a V-tokenomics boost on top. This is a very complex mechanism of interactions between very different users. And as a lending market, you have to always guarantee that everybody can be made whole, that the protocol is solvent, the money is there, and most importantly, no user is ever under collateralized. So how do we do this? We built a simulation engine, effectively, that simulates the whole logic of a lending market protocol, where we can generate users, fictitious and not, and the main inputs that go into a simulation of a lending market are. Does it work? Yeah, there we go. Are basically the price data histories for the assets on the protocol. So effectively, at the end of the day, the lending market is stressed by introducing price dynamics and see how the protocol behaves in different like price behavior regimes. You have user actions, which at the moment we don't consider to keep it as simple as possible. And last but not least, you have the actual users. Users are basically defined by this kind of density plot where, you'll see it in a second, that basically quantifies like the distribution of risk that users are willing to take and the distribution of portfolio sizes that they're willing to bring onto your platform. And then you basically stress test these users and you see which ones get liquidated, and you simulate and you model the whole liquidation behavior. Is there enough liquidity to liquidate these users, and what happens in terms of slippage, and you compute the optimal strategies for liquidators to liquidate specific assets of the users, and so on and so forth. And all of this depends on specific protocol parameters. In a lending market, the two main ones are the liquidation loan-to-value ratio that an asset has, and the liquidation incentive that the protocol assigns to assets. And so by stress testing the protocol, you can effectively iterate over different combinations of such protocol parameters and find some optimum that you want to hit. All right, so the inputs, as I mentioned, users. Users are defined by their risk profile and the amount of money that they bring on the platform. Shown here is a typical histogram of users in one of our simulations. We do many of them. This is just, you can think of this as one of them. It's a density plot. It shows that, on average, users have portfolio sizes of $10,000 and take on like an average user LTV of roughly 0.6. This kind of data is data that you can extract from on-chain data by looking at, for example, users on Aave, users on Compound, and you can see at any given moment in time what is the empirical distribution of user portfolios and user risk. And from that, we can effectively we can basically model that distribution and sample from that distribution, and we can generate as many users that we want for stress testing purposes. Then, the second input, price dynamics. Price dynamics can be generated a bunch of different ways, through simulating actual geometric Brownian motion, or by taking historical data and randomizing your starting point for the data, choosing to take different log returns at different moments in times and just stringing them together, or taking direct sequences of historical returns to effectively capture any potential correlation in price data that isn't obviously modelable. The point is that we can generate price dynamics and price histories in a bunch of different ways. Shown here is an ensemble of price histories with a couple of them color-coded, specific ones color-coded, just for visual sake. All right, and so we initialize users on our protocol, right? And then we simulate the price of the assets on the protocol, and we see who gets liquidated, who doesn't get liquidated. Shown here, for example, is like a back test on MATIC's worst performing day. This was November 26th of 2021. Actually, it's had a worse day since then, but the paper is from May, so this is what we got. And shown here, so in blue is the price dynamics, and the bars are effectively the liquidation events that we can simulate with our stress testing mechanism. I'm not going to go into the math, but if you want, read the paper, and we explain the whole logic of how you optimize, the kind of non-trivial optimization problem that liquidators need to solve to choose A, which user to liquidate, B, which collateral asset to repossess, C, which loan to repay, D, how much of that loan to repay. It's a non-trivial problem. It's not rocket science, but it's a problem that needs to be properly handled. All right. Oh, and by the way, one thing I didn't mention is when we simulate liquidations, we also simulate slippage on available liquidity for swaps. So liquidator typically will repay a user's loan, repossess their collateral, and then they basically repossess the amount that they liquidated plus some percentage that's their liquidation incentive bonus. And then typically you assume that the assets that they repossessed, they swap out of it to basically remake their original token back and keep the profit. So for this, you also have to keep into account what kind of slippage they can expect to see on just in general for swapping out of that token, and that goes into the whole optimization process for how a liquidator liquidates users. Okay, and shown here is like a protocol-wide like health diagrams. Okay, on the left you have the protocol LTV, loan to value ratio. In the center you have for a set of simulations the total liquidated funds on the protocol, and on the right the outstanding debt left over, and it's all color coded by volatility in asset prices. To keep it as simple as possible for presentation's sake, the assets are all assumed to have the same type of volatility except for stable coins, which is certainly not, it's not exactly reality, but it's close enough to make plots that you guys can look at very simply on a screen. The shaded regions are 95% confidence bands intervals, so we can effectively see how, for really, really high volatilities, the protocol loan to value, the effective loan to value ratio of the entire protocol goes down. This is typically the result of liquidations, which effectively reduce the outstanding debt, and in fact you can see that on the right also. And we can monitor all these things. And we can monitor these things as a function, potentially, of protocol parameters to see where we want to be. OK, so let's optimize for protocol parameters. Shown here is a graph of what we like to call the under-collateralization frontier. OK, so we basically ask ourselves, OK, we generate an ensemble of users. We run this ensemble of users through a bunch of different realizations of price dynamics, which are day long. We don't simulate longer than a day, because beyond that, you can't assume that users won't ever retouch their portfolio. So this is obviously an approximation, but you can think of it as as a worst case scenario. Like for 24 hours, nobody touches their portfolio allocations. And we ask ourselves, at the end of the day, what percentage of the users ends up under-collateralized? So just for reference and for context, we're using, in the price data, we're simulating 1-minute ticks. So effectively, any liquidation takes what will by default take place with a 30-block lag. Okay, this is on Polygon, right? 30-block lag on Polygon. So during those 30 blocks, a user that is already liable for liquidations, their health can get a lot worse during those 30 blocks, depending on what price does. Depending on how much worse their health gets, you could get into a situation where that user becomes under-collateralized. Big no-no. You don't want this. So if you want to avoid this, it's important to find where this happens. And that's what we call the under-collateralization frontier. Shown here on the y-axis, you have the liquidation LTV for a specific asset on our portfolio, on our platform. And on the x-axis, you have the liquidation incentive that we assign to that asset. So these are two critical parameters in a lending market. And we can effectively grid this entire plot and basically sample pairs of liquidation incentives and liquidation LTV, run a simulation with price dynamics with different volatilities, and we can see where this under-collateralization starts happening with a probability higher than 1%. The solid line you see here is the theoretical prediction that we discussed in the paper for where you are guaranteed to create under-collateralized users. So it was really nice for us to see that the simulated data and the theory kind of matched up on here. But why stop? And the theory is basically this: you never want your liquidation loan to value ratio plus your liquidation incentive always should be less than 1. In reality, it should be significantly less than 1. You never want to get close to this liquidation frontier, this under-collateralization frontier. But why stop at 1%? Let's make this more refined. If we're given enough computational power, you can do way more simulations. You can resolve way smaller tail effects in the stress testing. So let's check the probability of generating 0.1% under-collateralized users, right? So again, you have the solid line is the theoretical line, but now you see that the under-collateralization frontier moves further to the left of it. And if you were to keep going, again, given enough computational power, you could think of generating for any probability of under-collateralization, you could basically foliate this entire plot. And then it's a matter of choosing what kind of risk am I willing to take. Is 0.1% good enough? 0.01% good enough? Just in general, we stopped for the paper, we stopped at 0.1%, but we talked about this yellow region as being an area where you'd want to choose your values depending on the assets that you have on your protocol. And this is how you stress test the protocol. This is how you do not want to have too high of a liquidation LTV value. Why? Because then to remain safe, you need to have a really low liquidation incentive. And if your asset is, and if you have a really low liquidation incentive, that means the moment that asset starts getting toxic, liquidators aren't really incentivized to liquidate that toxic asset. Again, you're going to be in a situation where you create under-collateralized users. But why stop at the protocol level? Let's go to the individual user level. So shown here, I apologize if it's too small, but we picked 2 random users. This is actually from Aave. These are 2 random Aave users that we picked. And this is to show one very important point that we'd like to stress. Right now, lending markets focus their entire risk presentation around health factors. Who here has seen, knows what I'm talking about? Who here has used DeFi lending protocols and knows what a health factor is? Fantastic. It's color-coded, green, orange, red. You want to stay out of the red. You don't want the number to get too close to 1. It's scary when it gets close to 1, right? But the point is that that number is kind of stupid. I mean, it's not stupid, but it's a naive number. It's effectively a proxy of the loan-to-value ratio of your portfolio. But just because I have a higher loan-to-value ratio in my portfolio than someone else doesn't mean that I am a riskier user than that user. Shown here is a typical example of that. So we have, in green and red, we have 2 users. With different starting loan-to-value ratios. So red has a lower loan-to-value ratio. So in terms of health scores, has a higher, healthier health score than the green user. And this is their LTV simulated, their LTV and outstanding debt simulated over time during the COVID crash. So using the data from the COVID crash, right? What we start seeing is that the green user, which you can imagine is probably short crypto, does relatively well, whereas the red user actually gets liquidated, and we can see this in the cumulative liquidated funds. We can see it in the outstanding debt of the user, and so on and so forth. But we can go more in detail. We can look at these 2 users and simulate the actual distribution of their loan-to-value ratios as a function of different price volatilities of their assets. I don't know if you can see them; they're written really small, but basically all these plots are from lowest to highest volatility. We simulate from 3 all the way up to 50% hourly volatility. And then we can with this data, we can extract a quantity which we think is much more useful for users and for user risk dashboards, which is the probability of that user getting liquidated as a function of market volatility. And that's what you see here. Again, red and green are color-coded like the users earlier. And what you see is the probability of these users getting liquidated as a function of market volatility. And here's where you see green user, who, remember, had a higher loan-to-value ratio, lower health score, actually has a lower overall probability of getting liquidated on a lending protocol. And we think that, yes, health scores have gotten us to where we are right now, but it's important to really raise the bar on what it means to assess the risk of users, not just at the individual user level, but at the general protocol level once they all start interacting with each other. And with that, I go back to the framework figure that Amit introduced you to. So we have this model that effectively it's a risk assessment engine where we stress test we stress test the system to optimize for specific protocol parameters. That allows us to implement the risk management, basically based on the simulations that we do. We can monitor and review whether in real life that actually performs as expected, and then you start over again because the work never stops. You always got to keep going. And this is important for, again, parameter optimization, giving users more advanced risk dashboards to assess what risks they're actually taking on DeFi platforms, and last but not least, also inform DAO decision-making at the DAO level. And with that, I'd like to thank you so much for being here. If you're interested in asking questions, I don't know if we have time for questions. I'm not clear how exactly it works, but if not, you can meet me outside, and we also have a bunch of OVIX swag that we'll hand out for questions. You can read more at our paper here on the ovix.com website, and you can find us on Twitter and on Telegram, and we're very friendly, lovely people. Thank you very much.
Any question?
Thank you very much. Very interesting presentation. But I have one question regarding the last slide. So you mentioned a lot of health factors, but most protocols also have a second parameter. The interest rate doesn't capture. Doesn't the interest rate already capture this next to the health factor?
No, the interest rate captures, right now, actually, we could have a whole other conversation on interest rates, and we're working on a paper on that matter precisely. Interest rates really capture the amount of actively utilized capital on your platform. You don't want to utilize you want to incentivize utilization, but you don't want to incentivize too much utilization because then users can't withdraw their money. But at the same time, I'll agree, the interest rate does matter here in the sense that right now, these simulations that I presented here today, the users are basically uncoupled agents. We can look at individual users and assess their risk because it's a one-day-long simulation. Sure, in principle, there's interest rates on top of the price dynamics, but we're stressing high volatilities The bips you're paying over the course of 24 hours are negligible compared to these price volatilities. But if you want to simulate longer periods of time, where you then have to also model the behavior of users, which is a whole other beast, then yes, then you need to model borrower interest rates, because that's how users communicate information to each other about what they want to use or not use on your platform.
Okay, thanks a lot.
Any more question?
So yeah, my question is, you mentioned that your simulation matched theory, right? Mm-hmm. I guess the natural question I have in mind is how well are you able to predict the empirical data? So what's the performance in terms of predicting liquidations of users?
So on a 24-hour time scale, it's again, it's pretty good, but you don't want, but pretty good has to be put in quotes, because the point here is not to predict a specific event in reality. The point here is to predict worst case scenarios and create worst case bounds for how reality may unfold, and choosing your protocol parameters in consequence, so that then you don't care what actually happens in reality. You've simulated like worst case scenarios, you've quantified worst case scenarios, and you're prepared for the worst case scenario. This line doesn't happen in reality because nobody wants to get that close or that risky as a protocol. You want to add something to this?
Yeah, I think a very important point, you can clearly see theory doesn't matches, right? So this is the area actually where the liquidity in the market is less, the slippage is too high. So that's a deviation which occurs actually. So yeah, so it also depends, because if market is too much volatile, it also depends on the external market also, because in the DeFi, we are also liquidating on DEXs, like Uniswaps kind of thing. So that's one of the constraints which also DeFi faces. You hear like liquidations, right? Those are on-chain liquidations. So that's why. So if we see the Binance kind of a liquidity in DEXs, like probably it will match perfectly.
I hope that answered your question. But yeah, like this is like golden rule. Never get anywhere close to there. You will generate problems on a lending market. But luckily, nobody's really there. I mean, you'd have to like be really playing with like super exotic tokens to get that close. But it does tell you if you're listing a token, you can't just think, oh, what liquidation LTV will I give it? You also want to choose a liquidation incentive that is proportional to the risk that token brings to your platform. And you know, if your liquidation incentive is really high because you want that asset to be liquidated first, if anything weird happens, that already starts setting the bound to what your liquidation LTV should be. And so it's like it's this two-variable problem that needs to be properly assessed. All right, thank you very much.